All right, so today we're just going to talk about means and standard deviations. And ultimately, I need you to realize that these are the signal and the noise of your experiment. Now, first, what's a signal? The signal is the value you're seeking. Doesn't matter what you're measuring, it could be temperature, it could be happiness. You are trying to measure this construct, this object, this variable in the world. Your signal is your estimate of that variable, whether it's temperature or happiness. Your noise is the fact that everything you measure, temperature or happiness, is measured with noise. Is the temperature actually 72 degrees or is it really 72.6? Is your happiness actually strongly agree that I'm happy today or is it more like strongly agree point 0.2? Ultimately, the statistics and science depend on us understanding signals and noise. So this little graph may look familiar to any philosophers. This is the allegory of Plato's cave, but I've adapted it to statistics. Behind us, there's truth, and we can't see it. Our methods of statistics get us close, but we can't actually look around and see the truth. And this is the reality of science. We don't know absolute truth, not at all. We're trying to develop methods, the fire, the guys holding those sticks, that allow us to see the truth through the reflection, the shadows on the wall, which are our data. But ultimately, the important thing about this slide is that even with science, even with the best methods that humans have developed that allow us to find truth, we still can't perfectly see truth. We cannot be 100% certain of truth. So, my lesson to you is be humble and be persuaded by data, but also be a little sort of reserved in your persuasion of data. Now, what I mean there is that if you see something published, you don't just automatically accept it, right? But if you see something published and it's the only thing ever done on it, that's the only information that I personally trust. The only information that I believe that we should use to make conclusions about our understanding of the world, both in my personal life and outside in my professional life, is data. But we know no data is perfect, so nothing is infallible. So just sort of appreciate data, appreciate that the statistical methods are our best methods for understanding truth, but also they're not perfect. So we can't be overly confident. The signal in psychology and neuroscience experiments, true experiments, that's where we're going to focus most of our energy on, is the mean or both means. Are humans nice? This is just a question for today's discussion to give it some context. I'm just curious, are humans nice? How would I begin to answer this question? One very simple way is I just measure all the humans on this planet. And the difficulty here is that I would get a lot of different numbers. I would get, let's say it's a 1 to 5 scale. I'd get a lot of ones, I'd get some fives. Are humans nice? Well, ones suggest not at all. Five suggests they are. Do I choose 1 or 5? No. I average them all together because I understand that I am not measuring something perfectly. Each time I measure a human's niceness, right, I'm getting an estimate of that average niceness of all humans, of that true niceness of all humans would be a better way to phrase it. But ultimately, are humans nice? Right? Like I measure all humans. I have to figure out mathematically how do I take all this data and reduce it to one number. So, what is that number? That number is the mean. The mean you can calculate. Let's say I measured 4 people on their niceness, 1479. The mean of that is 5.25. Add them up, divide by 4. And you're like, okay, great. That's how you calculate the mean. But what is the mean? Those are two separate questions. And I want you to start separating them in your minds and in your actions because a lot of folks are just happy getting the correct answer. But stats is not a video game. Stats is not about conquering different levels and beating the boss. Stats is about understanding what you're doing. So ultimately, we say that the mean is the center of our data set. Well, what makes this the center or the balancing point? I think the balancing point is a better analogy. So our mean is 5.25, and I know my 4 observations. So I calculate how much each score deviates from the mean. Remember earlier when I was saying which number do I choose? I don't know, right? Like that was a very important question. Implicit in that question was the fact that each of our observations are measured with error. So these are 4 different people. They have individual differences in their niceness, right? I didn't necessarily measure them. Maybe it's personality factors, maybe it's other things, but these individual differences are going to impact how they respond on this questionnaire, right? And so what I'm trying to do is figure out, what's special about the mean? And so what we can see here is that my 4 is negative 1.25 units away from our mean of 5.25. Our 1 is negative 4.25 units away. Our 7 is 1.75 units greater than our mean. And our 9 is 3.75 units greater than our mean. I'm trying to figure out how the mean is the center of the data set. How's it the center of the distribution? What's it do? Well, essentially, it's the point where the values, where the deviations from the mean to the left of the mean are equal to the deviations to the right of the mean in terms of the weight. So if we look at this, each of these blocks represents a deviation score. That deviation score represents error in measurement of that individual observation when we compare it to the mean. The error in our measurement of that score, and the mean is the place where you have an equal amount of deviation to the left and to the right of the mean, or below and above the mean, or less than and greater than the mean. I will use those interchangeably throughout the course because I like colloquial language when discussing statistics. But ultimately, it's the balancing point, because the deviations to the left of the mean equal the deviations to the right of the mean. And you can see this when I put the red blocks and the blue blocks together. The red blocks are the negative deviation scores. The blue blocks are the positive deviation scores. They are equal to each other. The mean is the center value in the distribution. It's the point in the distribution where there's an equal amount of value weight to the left of the mean as there is to the right of the mean. Stated a little bit simpler, it's the place where the deviation scores sum to 0. That's the definition of the mean. It's the point in a data set where there's an equal amount of negative deviation from the mean as there is an equal amount of positive deviation from the mean. That's it. That's all it is. The sum of the deviation scores is 0. That's the point where the mean is. Now, there are alternatives to the mean that are focused on in a lot of stats classes. In this one, we're not going to focus on it so much because it's not important to how we actually do our science. So ultimately, the first one is just weird. Most common score. Okay. Like my most common score, you just look at the most common score, that's your mode. My question is, just imagine a data set where you're looking at the niceness and you have 4 most common scores, a 1, a 4, a 7, and a 9. What does that mean? My instinct is to try to average them together, but honestly, it's really difficult to understand what the mode by itself means without any other. It's not the center of the data set, it's just the most common score. It can be the center of the data set in some data sets, but it not always is. So it's not very useful. So bye-bye. Now, what we did with the mean was we found that centermost weighted value, right? Where the deviation scores from the mean on the left are equal to the deviation scores on the right. We put a balancing point there. It's the balancing point of the values. The median is the balancing point of the scores. You ignore the value, you list the scores from smallest to largest, and you just find the middle score. That's the median. Let me show you in an example. So here you can see the difference between the median and the mean sort of thinking. In the mean, and you'll see it again, I had the numbers spread out based on their value on the number line. Here I have the numbers spread out just based on their order. So this is sort of like if we ignored the values and just looked at the orders, that's the first step to calculating the median. And I'm saying ignore them, don't completely obliterate them, because we're going to need them. And our goal is to find the middlemost score. Now in this example, we have an even number of observations, so our middlemost score is going to fall between two scores. And what we do to find this mode would be 4 plus 7 divided by 2, or 11 divided by 2, or 5.5. But ultimately, it's a balancing point of observations. The mean is the balancing point of actual valued scores, and the median is the balancing point in terms of observations. It's the point where there's an equal number of observations to the left and to the right. So 1, 4, 7, 9, balancing point is 5.5. There's an equal number of observations, scores below and above. They were similar in value in this example, but don't let that confuse you or anything like that. We are not going to do our statistics on the median. We're going to focus on the mean, but I felt I should share it with you. I do think the median would be a good choice, but we'll talk about that another day. All right, so now, simple thought experiment, right? Imagine you're the first statistician. You have created and understand the data in the mean. You understand that the center of your distribution is your mean in terms of value, in terms of weight, right? You get that. You understand. We just talked about that, the place where the deviation scores sum to 0. We did talk about that already, but don't let that confuse you. You get it. You understand what it's doing. It's that balancing point in terms of weighted values in your distribution. Great. But you also notice that some of your numbers are closer to the mean than others. That is, there's more error in that measurement. Let's think about this for a second. Our estimate of signal is 5.25. We have numbers 1, 4, 7, and 9. Right? Why does number 1 differ from 5.25? I have no idea, but it does, and that difference of negative 4.25 is due to stuff I didn't measure, stuff I don't know where it's coming from, and what we do in statistics is we label that error. So error, we have error right there. That's actually pretty beautiful. For that individual data point, that deviation from the mean, that deviation score represents the error of that individual score, the error in our measurement of that individual score to be more correct. And you have 4 other scores. They have four measurements of error. And you're like, okay, you want to know how much error is in your data set. On average, how much error is in my data set? On average, how much do my numbers deviate from the mean? How much error is there in my measurement on average? That's the question we're asking. Another way to think about it, and I like using the noise example, you want to know how much noise is clouding your estimate of your signal or your mean. How much noise is there present, making it difficult to interpret your actual calculation of the mean. Because we are humble and we know that statistics aren't perfect, and so we know that true value we seek, it's very unlikely to be 5.25, but it's probably likely to be close to that 5.25. But in order to figure out how close we think it is, we have to understand how much error is there, how much error did we measure in our entire data set? Great question. All right, let's get to it. We know what we're trying to do, find the average error in our data set. So we're just going to find the average of those deviation scores, because those deviation scores represent error that we measured. We can measure this error. This is error. We don't know where it's coming from. We call it error. Let's find our average error. Negative 1.25 plus negative 4.25. That equals negative 5.5 plus 1.75 plus 3.75. That equals 5.5. And then we get negative 5.5 plus 5.5. And that equals 0. And then we're like, okay, that's our sum of our deviation scores. That's the first step in calculating our mean. We divide it by 4. 0 divided by 4 equals 0. And we're like, That seems pretty good. Seems like we have very little error in our data set. Huh. Do we have too little error? Wait a minute. Wait a minute. None of my scores are 5.25. Something is horribly wrong here. Let's look back and figure it out. What's wrong is that essentially because we have the definition of the mean, the place, the center, the balancing point of the values means that you're going to have scores that are negatively deviating from the mean and scores that are positively deviating from the mean, and they're going to be equal to each other. So that step in calculating the average deviation from the mean to try to calculate the average error or average noise in our data set is always going to add to 0 because you have those negative signs. We've got to get rid of those negative signs. That 4 is still a measurement of 1.25 units of error, but we got to remove the negative sign. So now we change from wanting to calculate the actual average to calculating the conceptual average. We still want this concept. We want to know on average how much error was present in our data set. We're going to look at our deviation scores because each deviation score represents error in our measurement of the mean. We don't know where it came from. We don't know why this 1 is less than 5.25. We don't know why this 9 is greater than 5.25. We just know that the difference there, that deviation score, is error. We also know that we can't just average them together, but we want a calculation that essentially represents the same idea. So how can I adjust my calculation so this doesn't sum to 0? Go ahead, rack your brain over this for a few seconds. Think of 2 options. All right, there are 2 potential solutions for this to find the conceptual average of our error, the conceptual average of our deviation scores, but ultimately there's one that we use and one that we don't. Now the easy way for me, I look at that data, I'm just like, knock off the negative scores and average those together. That's taking the absolute value, then average the absolute value. That would have been easy. Unfortunately, that's not what we do. What we do is this difficult concept that involves squaring the deviation scores, then taking the square root, but not in that order. Our first step is taking is squaring the deviation scores. We do some steps in the middle, and then our last step is taking the square root. So this process that we're doing is a conceptual average deviation score. And it works. The steps work. They're not the same. It's not going to work the same as taking the absolute value. It's not the same. Okay? So our first step is we square the deviation scores to get rid of the negative sign. Boom, that's our problem. Square deviation scores. That's where we start. We want to calculate the average. So our first step in calculating the average is summing. What do we sum? Well, we have squared deviation scores. So we're going to sum the squared deviation scores, and we call this the sum of squares. Next step in the average is to divide by the number of observations, in this case, the number of deviation scores, which are the number of estimates of error in each individual data point. So that's pretty simple. We divide by n because that's the next step in calculating an average. This is called the variance, and it's not the average deviation score, it's the average squared deviation score. That's the concept of variance. And this concept's going to come up a lot. And then finally, we take the square root. This gets rid of the squared units. That's the only reason why we're doing this. And thus, we get the standard deviation, which is a conceptual approximation for the average deviation score with the understanding that the statistical average deviation score will always equal 0. So it's an approximation of the same idea, but we call it standard deviation. And I think that's important. It's important to know why we're doing what we're doing. And why did we choose the difficult path over the easy path? I honestly, this is that'll be a question for a real PhD in stats. Like what we're doing is we're borrowing tools. And there are folks that are going to understand this at a much higher level than we do. The difficult piece that I found in sort of my career is finding somebody to explain to me in language that makes sense in my mind the statistical reasons why we do something. In my explorations of this question, I found that the standard deviation just has better properties in terms of discovering signals, essentially discovering the actual error. It has better properties. Beyond that, it's not worth the conversation today. So a standard deviation is just a conceptual approximation of the average deviation with the understanding that the average deviation is always zero. So I just want to go over the steps again. You start with your deviation score, score minus mean, because they tell you how much error is in each observation. Your deviation scores are the error in each observation, the error that each observation is adding to your signal. Okay? So your signal's your mean, the error from that mean, the difference from that mean, we don't know what to attribute that to, that's just error. We square the deviation scores to get rid of the negative sign. We sum these squared deviation scores, and this is called sum of squares because this is the first step in calculating the mean. Then we divide by the number of deviation scores, or squared deviation scores, excuse me, because this is the second step in calculating the mean. And now, because our number is in squared units, we have to take the square root. And when we do this, we call it the standard deviation. I didn't mention that the average squared deviation is variance. Variance and standard deviation are related. Okay, standard deviation squared is variance. Square root of variance is standard deviation. That's it. Down here, you can look at the numbers for a second, but ultimately, if you use the absolute deviation method and the standard deviation method, you do get different results. So I just want you to be aware of that. Conceptually, they're the same thing, but in practice, they're not. So don't use the absolute deviation, even though it makes much more sense to me and probably you as well. What does standard deviation mean? Well, let's look at a perfect experiment, one measured without error, and let's look at the effect on standard deviation. So first, it's a thought experiment. I made it up. I'm assuming like these super intelligent aliens exist. They have the ability to make perfect clones, and they have the ability to make a perfect experiment. So they make these perfect genetic clones with everything, epigenetics, everything that they know that we don't know, okay? The aliens that have personalities, they're fun like E.T. They never interact with the clones. They want to keep that completely independent of themselves. But the aliens did create rooms and robots and fun things that allow every single clone to have the exact same life history, exact same life experience, exact same experience of the manipulations. Everything's the same. It's a perfect administration of an experiment, and it's a perfect control of individual differences and time of day and all this other stuff. Everything is held constant. They measure niceness. What do they find? All four numbers are 5 1/4, 5 1/4, 5 1/4, 5 1/4. Their standard deviation is 0 because there's no error in their measurement of the mean, right? Is there error? That 5.25 is the value of niceness in humans in their study, right? You could probably limit that conclusion, but just ignore that for right now. Don't get too, it's for humans with that specific genetic makeup. Sure, fine, whatever. Throwing it out the door. But it's still a perfect study with no error. And when you have no error, your standard deviation is 0. So what you should realize here is that smaller standard deviations are better science because they're less error, more control in your data. And they're beautiful. So reduce your standard deviations. That's actually very good science. We know that having two drastically different means across our control and experimental group is good. I don't think we know that having two very low standard deviations in our control group and one in our experimental group is just as important and is equally as important in finding quote unquote significance or effects or things like that. So, just to reiterate, standard deviation is a measure of how bad your science is, how bad your measurement is, how bad your condition was administered, right? You can see that large standard deviations are telling you like, oh, something not right going on here. So, what increases standard deviation? Essentially, it's just poor data collection methods. For example, using a bad measure that has multiple interpretations. That's not great. Individual differences across participants. That's error in your data that you can't control unless you measure individual differences. So, like, there's error there. Cross-cultural differences in interpretation, historical differences in interpretation, stuff like time of day effects. Using poor, I think one of the ones you can control is using poor quality measures. Annoy the researchers that created the studies you are using and get their methods, get their questionnaires perfectly, get their manipulations, get their pictures, get their images, get everything, right? But using poor quality measures is probably the quickest way to increase your standard deviation because we don't know how they're going to be interpreted. So all of that leads to a higher standard deviation, more error in your study, and there's more than this. There's so much more than this. But yeah, that's how you do it. Take this point home. Smaller standard deviations equal better science because that's our measure of error in our data. And now we're going to pivot to start to interpret what is a good signal, what is a good estimate of error in an experiment, in a true experiment, in the simplest experiment. This is the simplest experiment I can present on PowerPoint. Somebody's at a computer with nothing on it, and somebody's at a computer with something on it, right? That's it. Simple experiment. I'm not even going to describe the methods anymore. Now, what is the signal we seek? And your answer is like, hey, Dr. Duricky, there's actually two signals here, like you were telling me earlier. I'm going to say, hey, student, in fact, there's really only one we care about because we know as scientists from the methods class last semester that you can't interpret your experimental condition without your control condition by comparison. And by comparison in math means subtraction. We subtract these two numbers from each other. We get a mean difference. That's how we do it. That's our signal. We don't have two signals here. We have one mean difference because how are you going to interpret the signal in the experimental group by not subtracting out the signal in the control group? The whole reason the control group exists or the baseline group exists is so we can subtract out, right, that random stuff. That when there's nothing going on, what is the score when nothing's going on? Like in a control group in my studies, I'm like, what is the average score of prejudice when I don't do any manipulation to try to reduce prejudice, right? And then my experimental group will allow me to know if I reduce prejudice. Without that control group to compare the experimental to, I don't know anything. And the only thing I know is the mean difference. And this is a fact that I think is lost on a lot of scientists even, but it's the mean difference that we seek. But this is becoming more and more common to talk about and more common to discuss. You have a mean difference. That is your one signal. Now you have two conditions. They had two different experiences. So it doesn't make sense to calculate your standard deviation by combining them together. So we actually have two estimates of error. One that's in the control group where everybody experienced that baseline measure or everybody experienced that control manipulation, whatever it was. And we have the second measure in our experimental group. And we're asking ourselves, why do numbers in the control group differ from the mean? Why do numbers in the experimental group differ from the mean? The answer is error in measurement. And guess who doesn't have that problem? Our buddy E.T. So now we have these signals. We have one signal, the mean difference. We have two estimates of error, the standard deviations in both groups. And now I want to introduce the idea of signal to noise ratio. And as we move on, you'll be able to interpret it. But right now, signal to noise ratio, signal on top, your mean difference on top, divided by your average standard deviation. That's the conceptual understanding. What you need to understand is that no scientist has ever measured anything without error perfectly, especially human behavior and neuroscience. None of the stuff we're measuring has been measured without error. And you're like, well, how do I know if my signal to noise ratio is large and good or small and crappy? essentially, there's different rules in different fields, but we compare, we essentially compare the size of our signal to the size of our noise. So if you have a signal to noise ratio of 1, that's great in psychology, but what it doesn't sound so great when I say it out loud means that your estimate of your signal is equal to your estimate of your measured noise as well. So when your measured signal equals your measured noise, that's amazing in psychology. Now in physics, when their estimated signal is 6 times greater than their estimate of noise, that is what they call a discovery in physics. So this is a common idea across different fields. But ultimately, the average effect in psychology is a good effect too for us. Maybe to any physicists listening to this, they're like, that guy's a bad scientist. Well, it's my field. We kind of have to deal with that. It's harder to measure individuals than it is to measure atoms or particles. But ultimately, if you have the average effect size in the behavioral sciences, which is 0.5, that means your measured signal is half the size of your measured noise. Or, stated a different way, your measurement of noise is double the size of your measure of signal. Same concept. You can do the math, right? Think about it. 0.5 on top, 1's on bottom. Your estimate of noise is on bottom. It's twice the size of your estimate of your signal, right? Your estimate of signal is on top. It's half the size of your estimate of noise on the bottom. Signal to noise ratio. So in the field of, well, it's not just psychology, it's not just neuroscience, it's medical research. Cohen's d is a pretty common metric now in the sciences that deal with human participants, and even sciences that are related to it. Not so much in biology or chemistry or physics, some of those quote unquote harder sciences. I actually think my science is the hardest, since I'm not measuring particles that are all the same, or chemicals that are all the same, or cells that are way more similar than people. I think my science is harder, but you know what I mean. So, but in psychology, we have something called Cohen's d, which is just the signal to noise ratio, the mean difference divided by the average of the 2 standard deviations. That's the conceptual understanding of a Cohen's d. Now, there's an actual mathematical understanding of the Cohen's d. What you're doing is you're converting that mean difference to a mean difference in standard deviations. So if I have a signal to noise ratio of 1/2 of 0.5, right? I know that my 2 means are half a standard deviation apart. That's what I know, right? That's if I have a Cohen's d of 5, my 2 means are 5 standard deviations apart. If I have a Cohen's d of 20, my 2 means are 20 standard deviations apart. Cohen's d tells you, 1, how many standard deviations apart your 2 means are. 2, it tells you the signal to noise ratio. Again, right? If your signal to noise ratio is 1, your measure of signal, your mean difference, is the same size as your measure of noise, the average of your 2 standard deviations. If your signal to noise ratio, if your Cohen's d is 0.1, your signal is 10 times smaller than your estimate of noise. Your measure of signal, your mean difference, is 10 times smaller than your measure of noise. If your Cohen's d is 100, your signal is 100 times greater than your estimate of noise. And in all 3 of these examples, in the first one, your means are 1 standard deviation apart. In the second one, your means are 0.1 standard deviations apart. And in the third one, your means are 100 standard deviations apart. So now we have 2 interpretations: standard deviations apart and signal to noise ratio. Cohen thought, probably rightfully so, that we weren't the brightest bulbs in the Christmas tree, and that we should have a standard interpretation of Cohen's d for our field. And he created that. He said 0.2 small, 0.5 medium, 0.8 large. I have my own called 0.4. That's my level of crap, and I'll explain that in a moment. Essentially, 0.2 is a small effect. When 2 means differ by 0.2 standard deviations, it's not real. It really doesn't matter. In 99.9% of the time, in the science that we're going to conduct, doesn't matter at all. You know where it matters? It kind of matters in the therapy side. Now imagine you develop an intervention It had a Cohen's d of 0.2. But if you applied that to 100,000 people, that saved 5 people's lives. I would say that saving of those 5 lives, while a small statistical effect, is worth doing. Right? And that's where sort of the Cohen's d stuff gets a little tricky when it comes into practice, when the practice is more than theoretical, when the practice is more applied, about saving lives, about, when is an effect small? Is saving one person's life small? If I saved one person's life in my life, that would be huge. I would tell people about that all the time. Like, do you remember the time I saved that one person's life? Right? So with that off the books, let's talk about science and publishing. If you have a small effect, they're going to like, that intervention isn't really effective, okay? So I'm going to stick with the publishing side. 0.2, small effect, doesn't really exist, not great. 0.5 is actually called a medium effect, but really it's the average effect in our field. So we're going to go with that, right? Like and that's a decent effect. If you're at the average effect size in your field or near it, that's pretty good, right? It's good to be average. It's good to be above average. This is the average effect of published research in psychology. If you're there, then your effect is just as good as the stuff I found or the stuff that other scientists have found. And 0.8 is a large effect. Notice that your signal is still smaller than your estimate of noise. That's how difficult it is to measure humans. Okay? Humans and cells as well. The average effect size in even cellular neuroscience is a bit higher. Cellular neuroscience, stuff with actual cells, with the neurons themselves. You got a little bit more control in that. It's about 0.65 from what I was researching today. If you find a better estimate, let me know. I'll give you bonus points for it. My level of crap is more one out of my own. I'm not going to pursue an effect that's smaller than 0.4. This has actually changed recently since I've started doing my research online, and I have it's not that costly for me to find effects that are smaller than 0.4, but still, when I find an effect size that's less than 0.4, I'm like, is it really important? Does it really matter? And for me, I'm like, ooh, that anything less than 0.4 is kind of pushing farther and farther away from the average effect in my field, and it's meaning it's small and small and small. And in my understanding of it, what I do, it means my interventions that are trying to reduce racism aren't that powerful, aren't that effective, aren't that great. So that's my level of cutoff. But ultimately, let's go back. What do we got? Standard deviations apart. Cohen's d tells you that. These two means, my Cohen's d is 5. These two means are 5 standard deviations apart. Still, Cohen's d is 5. My signal, my measured signal, my mean difference is 5 times greater than my measured estimate of noise, my average of my 2 standard deviations. Okay? And finally, 5 is a massive effect in the field of psychology. It's huge. It's real. It would be equivalent to what physics calls a discovery. And now your homework. Describe why the perfect data set has a standard deviation of 0. Go back to ET. Statistical average of deviation scores always equals one number. Give me the number. Standard deviation calculation is it the statistical average or is it the approximation of the statistical average? That should be easy if you were paying attention. In the standard deviation calculation, tell me why we do each mathematical step. We start with, and I just give them to you here. We start with deviation scores because they show us. I talked about that a lot. We square these deviation scores because we got to deal with a problem. We then sum these squared deviation scores because that's the first step in finding the average, and I gave you the answer, but copy it down. Next step, why do we divide the sum of squares by the number of deviation scores? Because this is very similar to the previous answer. Hint, hint. We take the square root. Think about it. Just humor me and calculate the conceptual version of the standard deviation shown here. Calculate the standard deviation of these 4 numbers the way I showed you how. In this simple experiment, what is our signal of interest? Definitely covered that. In a simple experiment, why do we have 2 separate estimates of noise? Maybe the better question is, why do I keep them separate? Right? Think about the difference between the control and experimental group. and why we wouldn't want to combine them. I talked about it a little bit. Give it your best shot. I won't be too mean on that one. Then let's just do your control mean equals 10. Your experimental mean equals 22. Standard deviation of your control equals 10. Standard deviation of your experimental group equals 2. You're going to have to average those two standard deviations to get your estimate of total noise in the total study. But once you do that, find the signal to noise ratio, find the Cohen's d calculation, tell me how many times greater the signal is to the noise, the measure of signal is to the noise. Is this greater than Dericke's level of CREP? Is this greater than the average signal to noise ratio in our field? And how many standard deviations apart are our two means? Finally, this question, give me 2 sentences on it. So what? Why should you personally care about standard deviations and means? Why do you care at all?